can we achieve, and I've tried to use very careful terms here, can we achieve some spectral information about all interesting LSST extragalactic transits? I don't throw in the asteroids here, I just wanted to talk about all the things that go bump in the night beyond our own...
there are stars in our galaxy that transit as well.
Well, this is the Cosmology of Galaxy work thing. Stars are seen as annoying interlopers. Alright, so just to give you the answer, I think the answer is yes to this question, and then the question isn't about giving up on trying to follow up all interesting extragalactic transients. It's about defining what type of spectral information, and then defining what is an interesting transient. So I would say we shouldn't have a debate about can we do it, it's a debate about what do we want to follow up. Okay, and then how do we do it. So I put this next slide in really to emphasize the point that was made earlier, that there are some incredibly interesting stuff out there that we will find. The transient sky is new, it's exciting, there are new events. Here is something that I don't know how many people are aware of, but only in the last 5 years we have discovered these fantastic explosions in the universe. We've run out of superlatives to give them, so we call them superluminous supernova. These objects are truly spectacular, as shown in this image here, in that here is the brightness of one of these superluminous supernova, and at peak brightness, these objects can go up to -23 in absolute magnitude. So these objects can in fact be four magnitudes brighter than your typical supernova 1A or type 2. So these explosions are extremely hard to explain in astrophysics, but they're out there. And the other thing that's spectacular about them is that if you look down here, the length of the light curve for these objects can last up to many months. So here are phenomena that 5 years ago we knew nothing about, and now we are finding in their tens through surveys like DES. These are incredibly energetic, long-lived explosions out there. And if you buy me a beer later, I will tell you how we're going to use these for cosmology, but I won't bore you with that right now. But this is an example of, we're going to look in the transient sky, we're going to find some fantastic new phenomena. So let's come back to more traditional supernova. So more traditionally, there's supernova surveys that are done through difference imaging. This example here is from the Dark Energy Survey, and the Dark Energy Survey is monitoring particular 3-degree fields. Each one of these fields is 3 degrees squared. So here's a configuration of 3 fields on the CDFS area of the sky. And we monitor these roughly every week, and we've been doing that now for the last 4 years. So in DES, we have LSST-like transient surveys already in the bag, and you can, but it's only over a few square degrees. So imagine this sort of data now across the whole sky. That is what we're going to get from LSST. And just to make the point that was made earlier in the week, we have to be careful about how we, the cadence of those observations, because we're now observing these fields once a week. Or if it goes less than that, you can already see once a week doesn't give you a fantastic light curve. They are good, but they are not as good as you can get. So I think we have to be very careful about how we dilute the cadence going forward. So this, after 4 years of effort with DES, this is where we're at with spectroscopically confirmed 1As. And unfortunately, it's not a lot. Okay, so if you're going to do a supernova survey and you think you have to spectroscopically confirm each one of those supernovae, I think you're going to find it extremely difficult. after 4 years of hard graft, trying to get time on tax, we are at 200 spectroscopically confirmed 1As with DES. But of course, in DES, we have many, many thousands of other supernovae. So in DES, what we decided to do is to take a very different tact, and that is not to try and spectroscopically confirm every supernova, because that is just truly hard work, but instead to try and get the host redshift for every supernova-like event. Yes. In this? So there it is. So far we've confirmed over 200 1As, of which of the order 15% have been other types of 1As. So, you can't follow up all your supernovae, but that doesn't mean you can't get some redshift information or some spectral information. So what we've been doing to get spectral information on the thousands of supernovae that are in DES is to really go after the host galaxy. So here what we have done is we've managed to secure 100 nights on the venerable AAT telescope with the 2DF spectrographs and the 2DF5 positioner. And what we do is, as DES goes back to these fields every week, we actually go back to these fields in spectroscopy every month. So every month we go back to these fields, we put the 400 fibers that are in these fields on objects, interesting objects, both active supernova, but also the host galaxies of previous supernova, and we build up a database of host galaxy redshifts for everything that looked like a supernova candidate. And I think that's quite interesting here, just to sort of pick up on Andy's point. Here we're very loose in what we call a supernova. So we go after everything that just looked like a real supernova candidate. We haven't even tried to classify it at this point. We have simply said it is rising, it's probably not an asteroid, it's probably not a star, we'll put a fiber on. So, and because of the multiplex of these instruments, you can do that. You don't really, you have the fibers available to be very broad in what you take a spectrum for. And we do the classification after the fact with the redshift. And that's the key that we'll come to. And just to sort of, this I really like for the old people in the audience, right, who remember, and that's relative, of course, older.
You think you're Nigel.
Well, we'll use Nigel as an example. Right? So, did you ever think, Nigel, the AAT would take a redshift for an object that is 23.7? No, is your answer.
Emission line redshift?
Sorry?
An emission line redshift? O2.
It is a emission line redshift from O2.
Yeah.
Right? But the point being is that through now with the AA omega spectrographs, who are stable, you can co-add spectra and still gain by the shock noise as you co-add the spectra. So here I'm showing an example of a supernova host that we've taken the spectrum for and we've revisited it multiple times. So the number of visits I'm trying to find.
The number of seconds are there actually, Paul.
Sorry?
The number of seconds. You put exposure times.
Oh yeah. So this is the integrated exposure time as we go to repeat visits again and again to the same object.
So they're pretty 1 hour exposures, probably.
Sorry?
They're probably
Well, 10 hour, right?
no, each visit is probably an hour.
Yes, each visit's an hour, yes. And some objects we go back to up to 15 times. And at that point we are still gaining by root T because we are no longer, because of the stability of these spectrographs, we are able to just keep adding the exposure time up. And as you can see here, there's no O2 in this one, but by the time you integrate it long enough, you can get it.
I mean, what's impressive for those of you who know with the sky, even up around 8,000, at the red end, the sky subtraction is working, unless it's been masked out.
So, to To give you a sense, we've now observed over 1,000 supernova hosts through this way, and we are on course by the end of DES to observe nearly 3,000 host galaxies of supernova events. And a lot of those are down, we've got some of those down to 24th magnitude, which again, for a 4-meter telescope, you would think was impossible a few years ago. But because of these new fantastic stable spectrographs, you can actually get down to these sorts of magnitudes available. So what we are doing in DES is we're doing the bulk of the objects through the AAT, and then we target the more interesting sources with the 8-meter telescope time that we have. And it is through this sort of combined approach that we will be able to get thousands of supernova from DES and be able to use them for cosmology. So, as you can tell, my proposal is that what we're doing with OSDES at the moment, we can do with the combination of things like Foremost and DESI on the LSST to be able to build up databases, spectral databases, of many thousands of supernova events, many hundreds of thousands of supernova events from LSST. And there's a team that we've, a loose team that we've put together, mainly here in Europe, but now that we're all part of LSST, please talk to us. But as part of this team, we have been talking to the Foremost collaboration, and I'm proud to say we have managed to now secure, so this is guaranteed time, we have this in the bag, we have guaranteed 250,000 fiber hours for dedicated LSST transient science. So what's good about this, and why we pushed pretty hard to get this allocated up front, was that now we can think about how we can use it, rather than thinking about how we can sell it to Foremost, and what proposal we need to write, and how do we get a TAC to allocate this to us. We have got it pre-approved, which means we as a community can start thinking about how is best to use this allocation of time optimally to follow up LSST transient science. And we are allowed to think about active follow-up, so we can follow up transients again if we can get the bureaucracy, if we can get the mechanisms working in our favor. We can follow up active transients. There will be a host of hosts, excuse the pun, there will be a host of host galaxies that we can follow up, so those can be secondary targets we can include in the follow-up. And one of the things that we did want to make sure is Foremost plans to observe the LSST deep fields as their calibration fields. So one thing that you might be interested in is Foremost will observe the LSST deep fields on the cadence of once every week. They are guaranteed in their plan to go back to those deep fields once a week. And we have asked, can we think about having some fibers there to again follow up, maybe again with the OSDES model, to follow up the higher redshift supernova hosts through the stacking of multiple observations of the same object. So that is again something that we can discuss and we can propose that we use. So again, my proposal was that we would gain redshifts through the multiple observations. Just to maybe stress, you may have heard me say it yesterday, I think this is a paper we wrote last year about the issues to do with a spectral classification with and without a redshift. I certainly agree with Naranja that when you just look at classification, the addition of a supernova host redshift doesn't really change the success rate. It gets slightly more successful if you have the supernova redshift, the host redshift, but in broad terms, the success rates stay roughly the same. The key, though, is what those populations look like after you've done the classifications. and this was a point we raised in the second half of the paper, in that if you look at things like the salt light curve, the salt 2 light curve fits to those supernovae, you do see without the spectrum that those salt 2 light curve fits are systematically biased in terms of the photometric redshift they return and in the colour they return. They are redder supernova than if you've had the spectrum. So my contention would be, and we made this contention already thinking of things like the LSST, my contention would be is while the spectrum may not help you significantly in the classification of the object, it is essential to have it to get unbiased distances and unbiased cosmology from it.
So you have a bias that's a function of symmetry.
Yes.
So it's not in the astrophysics, it's not in the templates, it's something about the way you're doing the methodology of the sets. Doesn't it have to be?
So my feeling is, and Pierre raised this, is that when you've got a low signal to noise sparse light curve, you're simply asking too much of that data to do both the redshift, the salt 2 color and stretch, and the classification. And what happens is those are degenerate, and what happens is it will give you an answer, but those answers tend to be biased. It tends to want to have redder colors and a lower redshift.
There has to be a technical problem that smart boys like you down in Portsmouth can solve.
Or girls.
Or girls. Probably girls, now you mention it.
Right, I will go out and hire some smart girls. Right. Beyond that, another reason to get a spectrum is that there are some extremely important supernova host correlations that if you are not including in your cosmology, you will again get it wrong. So there are other reasons to understand the supernova host galaxy correlations why getting spectra are important. So my take-home message from this slide is that while you think you may be able to do it all in photometry, you can do it a hell of a lot better if you've got some spectra.
Can I make a quick comment on the counter to that is we thought supernova 1A recently we were looking at time construction events. And actually when we look at the spectrum, we can say that it's we caught an early 1A at either plus 3 days peak or minus 4 days peak. And actually from that spectrum, that's degenerate. And so we actually need the light curve to break that degeneracy. So it's true we won't have spectroscopy for all of our transients, a tiny fraction of them. And I think the interplay between both of these is really important and interesting. And LSST will give those beautifully sampled light curves if we get the cadences right. So I think as someone outside of the field, I would really like to see sort of the communities that are wrestling with this at the moment really figure out what can we get from the photometric redshifts guided by the spectroscopy. Is that a problem that we can solve, or do we just have to accept that we'll do some statistics at the end of the 10 years, but without a spectroscopic redshift, then those light curves are not useful or are they useful? In our experience of this particular supernova, it's the light curve that we need to break the degeneracy of the spectroscopy.
So the reason we went out and got these spectral resources early was to have exactly the sort of conversation we were doing. So we are in a very interesting period, right? We can still debate the cadence in LSST, right? We're still allowed to put forward changes to what we think as a transient community would be best. And then we've got spectroscopic resources already on the table that we can factor into that discussion. And it may be things like, because we've got this spectroscopic resources, we may want to do this slightly different in LSST. And likewise, as we change potentially the LSST cadence, we can adapt the spectroscopic resources. So the cool thing now is that we don't have to worry about writing proposals to tax. We've got this time in the bag, and I'm very keen for the LSST transient community to really engage in this and figure out how best to use this 250,000 hours. So I've already done that. said this already, so forgive me. So I think it is now a question about how best we use these resources. There are simulations on the LSST side about how we optimize cadences and things like that. There are certainly foremost simulations, so I think some of the work that we could do as a community is how do we use these two sets of simulations to work out what is the likely overlap in time, area, depth. How do we trigger these foremost finders that we want to use? What are the best host galaxies to target? Are there other objects we want to target? In fact, we may not need all 250,000 fiber hours for supernova. I think we will, but we could. We may have a few spare finders over. We may want to do reverberation mapping of quasars. We may want to put in some photo Z calibrators that just to fill out, just to have backup targets that if we don't have supernova in that field, we can go and do other things. I think the opportunities of the synergy between the LSST deep drill fields and the foremost could be extremely interesting. And finally, I should put my hand up. I am co-chair of the DESI Time Domain Working Group, and we are having exactly these conversations with DESI about the opportunities to feed interesting targets into DESI to do the sorts of transient science that we're talking about here. So while DESI is in a different hemisphere, I accept it will not be as important as foremost. DESI is a very interesting multi-object spectrograph, and I think the combination of DESI and foremost could really deliver many hundreds of thousands of spectra to LSST. So I'll finish with this. I think I've answered my question. I think we can get some interesting spectral information on all interesting LSST transients, and maybe the key question in the next few months and years is what do we mean by important LSST transients? How do we pre-select those so we can give them to foremost or DESI that they can follow them up? So that I'm done.
Okay, questions for Bob?
So can I ask a question? Tidal disruption events. My understanding is that LSST will find hundreds.
Possibly more. I guess we don't know. I mean, we have 2 confirmed high energy ones, so it's easy when you catch them in the gamma rays, and obviously they're relativistic deep ones. I think a small number, 1, 2, maybe 3, found optically with things like PTF. I think Pan-STARRS has recognised the difficulty of finding weird things. I think they expected to find even more weird things. In terms of real-time follow-up with weird things, that was something that they found a real challenge. The difficult thing compared to things like gamma ray bursts is that they sit necessarily on a host, particularly as a contrast issue between a nuclear flare and a central bulge. So I think we have a fairly poor idea about the parameter space. We hope there will be many, and I think we also don't have a good feeling for the whole type of the galaxies that will show. So this is completely uncharted territory. The astrometry is also very important. I mean, we were lucky when we followed this galaxy up recently. Well, unlucky in the sense that it was actually a supernova that was about half a kiloparsec from the nucleus in the end, and it had a very small bulge as well, so we were able to resolve those two and do all of this imaging spectroscopy polar emission at 2 meter big flare to 15th magnitude from 90. So I think when you're looking at faint type disruption events against bright bulges, that will be a challenge for us. And I don't really have a feeling, maybe the LSST team can give us more of an idea about how they're planning to deal with this. In the difference imaging is probably where we're most successful at finding them, but it will be that contrast problem. So I presume you have the models of the galaxies and then you can find the contrast. If we then want to follow up a tiny fractional difference in the brightness, then that becomes more challenging.
Contrast problem. There's a flux of difference between the brightness of the galaxy. So you want to put a cut on how much the
supernova cosmologist, I just
say
want,
cosmology,
as supernova cosmologist, I just want 1As, right? And I'll plot the same trials but, as you're aware, in the supernova game, the zoology of supernova has exploded, excuse the pun, in the sense of these very different, the underluminous ones, the 1AXs, the superluminous. So I think that's an interesting area for LSST, is that we will get fantastic statistics on all these different types of explosions that we've only got handfuls of now. So, and again, it might be that this follow-up isn't specifically about doing a Hubble diagram. It might be about that half of it could be used for all that zoology of different types of energetic explosions that are happening. So I think there's a wonderful opportunity there for the astrophysics of those explosions.
Yeah, I didn't say it wasn't interesting, I said it might be easier than TDs.
So I have another question from Alana. So what has been the discussions in LSST about spectroscopic follow-up of transient objects?
Within the project, none, because we're not paid to do science. Within the science collaborations, Luciane will be the person to answer that. I'm not trying to avoid the answer, but the LSST project itself isn't allowed to even think about it because it gets slapped down again. Because for the construction project, and I will say for operations, it's different, right? So I think, I'm not the right person to answer this question because I haven't been paying very close attention. I think everybody says, oh, we need spectroscopy. And there's a new instrument going on Gemini South, which is supposed to have be a good follow-up instrument for a single object.
Yeah.
Spectra. But I don't think we have an answer. I like running 50 kilosecond per hour, isn't it?
Well, my suspicion is so, we can do large-scale population studies of brightish objects using the methodology I described. There will be interesting tens of objects that will require 8 meter, or there are, I don't know if people are familiar with SOX. Does anybody heard this is called the Son of X shooter, which is it's going to go on the NTT, and that will be again a single object but very rapid follow-up. So if LSST finds an extremely interesting single object bright source, SOX will be absolutely superb for getting a very wide spectrum of that. So the idea is to get from the UV all the way to the infrared at high resolution. So I think there are those sorts of opportunities for single-ish objects. But this is more about harvesting the bulk population studies.
Okay. Thank you, Rob. Let's move on to Robert. And Robert will tell us about the LSST camera. And again, ask any questions. We have a short talk on shell galaxies. Is Nichol in group? So we're going to start. Nichol.
Use my own.
That's the one there. Yeah, I don't want to steal that one. That's theirs.
Yeah, I'll do it. Okay, well, at midnight, I realized I was supposed to get a chocolate one because Yelko reminded me. He gave me a title, but I haven't given him a gift. So this was bad. So I went back and discovered I had immediately to give a talk, so I couldn't get out of that. Do it on a different topic, which is a little bit easier, so I wrote that. I think it's hard enough, this laptop's going to kill off, but they don't, so it's totally. So somewhere in here. Come on, brain dead. Just like to use
manager on the camera, who was a short lady, took over. She insisted that the picture of some Mario scale person on the side of the picture be removed and replaced by somebody who's 1.65 meters high, namely Nadine. Seemed reasonable to me, as the original person who was 1.93. I don't get that. So it's a big camera, 3.1 gigapixels. Mario, not Mario, the other one, Joko showed this figure earlier. So this is a filter complement. He said it's slow light, here are the slow filters. So really, the Z is very much better. We're using 100 micron thick deep vision devices. There are two Y bands out here. We're using the so-called Y4, which is down in the middle of this water vapor absorption band. I don't think that's a problem. We don't do that. Photometric chips are. Okay, so CCD. That's what the CCD looks like when it's still on its chip. We're using 4K by 4K devices with 16 readout channels. So this is one amplifier, that's another amplifier. We're reading at 500 kilopixels per second, I think. The French will correct me if I've got the numbers wrong. So the total readout time on the chip is 2 seconds. Those are some mock-ups. That's a picture of the focal plane with the required move here. Selecting more realistic, that's a production CCD. I can't remember whether it comes from vendor 1 or vendor 2. I don't think I'm allowed to tell you who they are, but you will know. It's a nice black chip, that's a good thing. Here's a production chip from one of the other vendors. You can't really see the chip so well, but I'm sure it works. And there, just to prove that we're building more than chips, is the silicon carbide support structure that I showed a picture of. So we put 9 CCDs into each of these cells. The wavefront and guide chips go into these cells, and that's the fused at 1,000 centigrade and things are going on. Okay.
So Rob, can I ask a really naive question? I've not followed this out of the zone. Are these prototypes or
These are production chips.
These are production.
These are chips. They may go into Comcam, but they are chips that we could put into the camera. They meet the spec.
Okay.
Yeah. That's why I showed you those rather than. It's the first time you should have seen real chips. I could show you pictures of lenses and things like that as well. I thought I would skip some. So yeah, this is real hardware that will be on the mountain. That's good. That's fun.
Yeah, no, it was like that.
Rah. Yeah.
I've seen far too many prototypes.
So have I. And that's why I wanted to show you some real chips. Here is a picture I made a while ago. This is the Cam pixel. This is the LSST pixel. This is just to remind you that these CCDs are incredibly thick with respect to the pixel size. And though this is now old hat to the people like Pierre, maybe you're not all quite aware of all the issues we have. Those of you in DES will be familiar with this problem, which is that you get these so-called tree rings. Those are due to doping gradients in the devices. This is Hyper Supreme Cam. I don't have the corresponding pictures for LSST. They're much weaker. As is well known in DES, you see this in the astrometry. They're significantly worse even in DES than HSC, and they're probably going to be worse in HSC than in LSST. Cosmic rays look different from the cosmic rays that you're used to. This is an electron track. That's what happens if you run the software on it, and that's what happens when you run the next stage of the software on it. There's no real problem with these cosmics. That's a muon track. You see these as well. You'll notice that the track's thicker at this end than this end. That's because these devices are so thick that the charge of diffusion, this is a CCD, a muon going through the device, entering the device at this end and exiting at that end. So this end, this is further away from basically from the pixels. This is the top of the silicon. There's more charge diffusion. So you're seeing charge diffusion in the device, and you're seeing more of it at one end of the track than the other. So that's a characteristic feature of these chips. The image quality budget is, I think, in the case of LSST, set by the fact we're only putting 60 volts, not 60 kilovolts, 60 volts across these devices to suck the electrons down into the well. They're also not a problem. So, cosmic rays are one feature of these devices.
So, Robert, just to remind me, what's the ratio? Is that just because the pixels are very long? It's the depth.
Yes, it's the depth.
So what was the ratio of the size of the pixel to that back? What's the ratio again? How many pixels?
10 to 1. There's 100 micron thick devices, and we're using 10 micron pixels. This is the World Trade Center, which is no longer there, but it was less skinny than the pixels we're using on these devices. It took me a while to make this figure because I didn't dare put a picture of the World Trade Center up in the US because I'll get into trouble. But I thought it was safe in this case. Okay, another feature that many of you will be familiar with is the point spread function is a function of the brightness of the stars. So these are stars, this is again also a hypersupreme cam, which is again very similar. They're 15 micron pixels, 200 microns thick. So this is stars, 1600 stars at 20th. This is 700 stars at 17th. They look like little spots. The stars are boring, they look like spots. But if you subtract the PSF at 19 from all the others, you discover that you get these holes. If the stars are thicker at the bright end, that's because of electrostatic effects with the devices. We have to be aware of that. It's going to mess up our PSFs. We know how to deal with most of it. It's what happens on modern CCDs. It's going to be a problem incidentally with sky subtraction in the red on CCD-based devices. It's almost certainly there in the Kaviraj as well. It's one of the things that makes me suffer on trying to understand. Okay. LSST is in fact doing some very extensive simulations. This is the picture of, and this bar is a constant size, showing you all the effects that we're expecting, at least someone was expecting, to be in the image quality for LSST. The optics are pretty good, the tracking is pretty good, the diffraction is irrelevant, the lenses are irrelevant, the mirror sort of splays light out bits, is still 0.2 of an arc second. The detector, this is the diffusion. The dome seeing is, I think, significantly underestimated in this picture than the atmosphere, even though it's polarization. So we can actually do quite sophisticated simulations. Andy knows a lot more about them than I do. But if you want to get these detector effects simulated, at some level the atmospheric effects simulated, we have a simulator which should do that. Yes, Andy? You stand by that statement?
Yes, we're still working to sign off on the actual sensor effects, but there's a lot of work with Craig Lane and others who are getting very close to being able to reduce the latex effect.
Yeah, there's no bright factor effect in here. These electrostatic effects distorting the effective pixel size are not simulated. Okay, just to remind you, you can't see that, you can look at my screen. That's the equivalent of about 2 years' worth of LSST data, taken in fact with hypersupreme cam. And the reason I'm showing you this is partly because it's very pretty when I look at it here. The other is that I'm going to show you some images to show you some of the troubles that we're having on hypersupreme cam with the blending at the moment. It's extremely interesting, I think. I think it's the hardest unsolved problem with the LSST project. And this is all the data that we have. I'll just remind you that that's the photometric redshift by eye plot. The red things you're seeing are redshift around 1 in that figure. So we're looking at characteristic objects at redshift 1. It's a lot deeper than slope and a very different regime. Okay, Mario went over this. I don't know if he showed any of these figures, but for you Galaxy people, we are going to be characterizing the data in terms of models, because I truly believe in statistics. So we'll be fitting moving point sources, that's what they care about over there. Something like a double Sursix model. Exactly how we're going to regularize that is not clear. Different people do it different ways. It's a really nasty problem. You have to do something beyond Sursix fits. It'll be something like a bulk disk model, but how many parameters get freed up is another very good question. We're planning to report the maximum likelihood and some samples of the exterior for those fits. We'll measure centroid, boring things like that, electricity, aperture fluxes, protein, probe, and radii. Colors, some seeing independent measure of the object color. That's a very complicated statement, of course. What you mean by colors for galaxies is not entirely clear. There are many different definitions. What we're planning to deliver to the collaboration is at least one color which is representative of a stellar population of the same redshift as this object. That's a somewhat carefully phrased statement. You don't necessarily get the best photometric redshift from the total flux, the total color of the galaxy. It can be very hard to measure. And in fact, it may not be what we want because you get a better photo set from the nucleus. I think what was spoken about there is quite good. So exactly how we do the radial weighting is not entirely clear to me at this point. And we'll have to pay quite close attention to that.
Sorry, Robert, can you say your statement again? Because it went past me pretty quick. So
Well, I can speak more slowly and more loudly if that would help.
it probably will.
Yeah. Okay, so if you have a galaxy and it's nice and bright, you can put a very large aperture down, capture all those photons, add them all up, and that will give you the total flux in band, in G band, say. You then go and take an image of the same galaxy in the R band, you put the same nice big fat aperture down, and measure the total flux, and those two measures of the flux give you the total flux of the object. You use that for cosmic star formation sensors and studies. And the difference in the two fluxes gives you color. Okay, great, no problem. The first problem is you can't actually put down a big enough aperture to capture all the flux from a devoted or associated n equals 6 galaxies. You have to do something else. And these various different sorts of measurements, like Petrosian and microfluxes that are currently using HC, are ways to define an aperture which we measure some fraction of the flux. You can also use model fit fluxes, which actually do a better job, but they're trickier. But they're in some sense the maximum likelihood estimate for the flux in the object. So that's all very good. Now, in reality, objects have color gradients. So how do you deal with color gradients? And in particular, that's not a problem if you deal with measuring the total flux. If you measure a non-total flux using approaches like this, with seeing present, then you're getting quite complicated answers to exactly what we need. Okay? So, if you have no color gradients, if the seeing is the same in all the bands, then you're essentially doing this. For example, if the seeing were 0.78 seconds in all bands, I can put down any arbitrary aperture I like, and I can use that to measure two fluxes in two different bands. And the color measured in that aperture is the color of so many square kiloparsecs of the galaxy. It's not necessarily the total color of the galaxy. Now, if I feed that color into photo Z code, it will give me the correct redshift. Because it is of an object, it's a different object, just some of the stars in that object. Okay. Now that's not true either, because your photometric redshift code has, of course, to be trained to handle the n of z for the population that you're building. And I've just chosen my definition of n of z different. So things get very tricky. So what we will do is to build an A color, which is insensitive to C, in ways TBD, because there are trade-offs between signal to noise, between what Hiranya was describing in terms of accuracy versus precision. And exactly how we're going to do those trade-offs is an open question. It's not just a question that I can answer, it's a scientific question. And we're going to have to iterate in ways that I haven't figured out yet in the scientific community. I think what will actually happen is that Jim Bosch and I will come up with some proposal, we will implement it, we'll run it on HSC data, and we'll say, how does that work? How tight is the red matter sequence using this algorithm? And one of the reasons why I designed this plug-in architecture for the LSST pipeline is that you can say, I don't like your algorithm, I'd like to run a different algorithm in parallel to make comparisons easy. It's relatively easy to say, do it this way and do it that way and see what happens. It's not entirely true because of things like seeing convolutions and deconvolutions and how simple your models are. But it's tricky. But that's what I'm getting at. Is that too long an answer or do you want me to expand it?
No, that's great. But I have another question from Allowed. I guess it's discussion. So,
Yeah.
So we've mentioned about measuring colours, optimizing potentially for G.
Not necessarily what we want, right?
So, well, my follow-up question was, my understanding is the lenses are also very interested in PSFs as a function of galaxy color gradient. So
No, other way around.
It's the other way. Okay.
They're interested in the influence of the shape of the effects that make that give colour dependent upon spread function. One is that just due to the commutator of turbulence of the lambda minus thing, so the seeing is slightly better in the red than it is in the blue. And that is pretty, theory said minus effect, that's actually pretty good usually. A worse problem is there's no atmospheric dispersion corrector in the LSST, something that I may or may not be partially responsible for, but I certainly regret that we didn't jump up and down loud enough. So that means that the PSF is smeared by the atmosphere, and that's actually, I think, a bigger effect. It's a real nightmare for the difference imaging. Fortunately, A, they can in the next door room, and B, it's Hunley's problem, not mine. So that's good. So we will model the PSF as a function of position and result. And when we're doing these model fits, which have to take into account information across the bands, there's no reason why the individual components can't be used with the PSF, the color of that component. I imagine we can do that. Now, that assumes that you could represent color gradients in galaxies in terms of multiple components. And I think that's usually the right way to think about it, but I think it's the only way to think about it, otherwise it makes your head hurt. If you have a continuously varying color, if you do an elliptical metallicity changes, that doesn't work so well. If you're thinking about sigma, any sigma noise, 30 objects, the best you can do is to worry about the bulge, this gray color grade. That's what you typically see. And that is quite well modeled as two components. Now, whether you can put enough degrees of freedom to fully do that is why I'm saying, what do you do? I mean, lumps, where it's bending ties, the bulge and disks, sizes together, for example, that the amplitudes split. So there are things. Does that help now? But it's not just for bending, that'll get you the correct photometry as well. Are there any other questions? Because I think I was going to go on to talking about the thing that I think you should be worried most about if you're doing galaxies, or in fact anything that's not transient. So you're safe with it.
I'll just do my email.
You can do your email, yeah. Which is dependent. So here's the problem. You can probably see that. I can't bother to get that closed out. This is an image from HSC, and I think it's from the wide survey. So this is like 2 years of LSST data, something like that. And this is a cluster. The red cause because the seeing was significantly worse in G when we took this data. There is some bad G back there. This is one single object, all merged together above an isomorphic level. So it's the job of the inventor to take that and say, what I know what that is. That's a combination of this object plus this object plus this object. That's not so bad. Plus that object plus that one plus that one plus that one. And in fact, that's just another example. So these are generic problems. Here's a simple one. I'm sorry that's fuzzy. That's the fault of OSX. I should really fix it. So that's the sort of thing you're dealing with. This is 1, 2, 3, 4, 5, I think maybe 6 objects. And yeah, 1, 2, 3, 4, 5, 6, I got that right. That is a combination of 6 objects. And the code that we're running now does this. It says, take that apart from something that looks like, this is the original object. Take it apart from this plus this plus this. And if you look at my screen, you can see the other things, it all looks okay. So this is the basically what we ran in the SPSS. So that's just fine, there are positions and centers, all is well, works pretty well for things like this, or that, or that, or that, so everybody's happy, except you're not. And the reason that you're not happy is partly because things that go wrong even at Sloan depths that mess up some of your interest in your galaxies. And this is an example. Here's an iselliptical, but there's a background cluster of galaxies, an object here, and 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 here. And when you run the deep blender on that, you end up with this. And all you can see, I can't remember if I zoomed in, is here's the original one, and you end up with something like this. But the little background things steal flux out of the way, the low surface brightness wings. It's kind of hard to get around that. I'll talk a little bit about approaches coming up. So one thing is that if you're aggressively, if you're running a reasonably sophisticated blender, which I think you need to do, based on, go back and look at other pictures and say, do you really want to treat that as one object? Then it's a hard problem, though not an insuperable problem, not sort of steal flux from the outer parts of CD galaxies. And if you're interested in CD galaxies, that may be a problem. It's a serious problem in Sloan. That was also the background subtracting wrong in Sloan. I have ideas on that. Okay, here's another example. Again, here's 1, 2, 3 points in the galaxy plus some extra bits and pieces. And that gets taken apart like this. And that's not so bad. You take this thing apart into this plus this plus this, and I'll zoom in on that. You end up with children that look like this and that. Okay, that's probably not what you'd have done by eye. Now, maybe it is. But there's some sort of extra stuff left over here. We haven't done a great job. It's hard to do a lot better than this. If I can do this well on every object in LSST, I'm going to declare myself a clever boy and go and retire or something. Okay.
Is that a promise?
When I get to that point, I'll retire. Or did you mean the first time? Yeah, sure, I'll be glad. Nobody else will. Okay, here's another object. This looks pretty innocuous, and the answer is that you pull something like that apart into this plus this weird thing, which I might claim was a Panarov-Riley class 2 radio source observed in the optical, but I'm afraid that I'm not going to get away with that. So
Robert, I have a question.
Yeah.
I mean, one of the things I do when I do outlier searches, and you have your catalogs, is you don't know what the software has done. So if you're deblending, if one of the products was the actual reasonable pictures, right? In some sense, does that make sense? So you then know.
Oh yeah, you absolutely have to get those. So I'm actually fighting our database group at the moment.
So having these secondary, well, I guess intermediate products, I think it will help.
I think you
understand.
Yeah, you absolutely have to have that. We had it in Sloan, Thermodynamic refused to serve it. It was a real nightmare. When people had problems, they would come to me and I would run the code and say, this is what I actually did.
Okay, okay.
This screen, there we go. So, this is an intrinsic problem to the algorithm I'm currently running. I think I know how to fix this one. But you're going to get corresponding things. Things get worse. So that's just to remind you what's going on. We should go over. The way my algorithm
just back up, because it's not in Mario's list of data products, I believe.
No, it's not a data product exactly. It's whether we serve the images of the children as well as the parents. And I think it's absolutely essential because, well, I'll get on to that a little bit in a moment. There's a dispute about how it. If I don't answer the question, Richard, bug me again a little bit because I agree with you, and I'm
I need a fan.
Yeah. So here we go. So what's going on here is that I didn't tell you how this algorithm works. And the way this algorithm works, and I've got some slides I wasn't going to show, they're in the backup slides, is to assume that every object has a, let's go back to a case that works a bit better. It's easier to explain. In this case, it assumes that every object as defined by these pluses in here, that each of these objects has a twofold rotational symmetry, which means that that pixel is the same as that pixel, and that pixel is the same as that pixel. And it turns out that by using that very non-parametric model, you could build an approximate model for every object. Because if you also assume that objects are positive definite, so that means that when you look at this thing, you look at this object and you say that pixel is the same as that pixel. But actually you take the minimum of the two, because you assume any contamination is positive. And if you do that, you can take this pixel and this pixel and say, the correct value is here. And you build an object that looks basically like this. Then you fit those models to the data and you split the flux up by the ratio of the flux into two different relevant models. And that is a sufficient assumption, that is a strong enough model in the case of things that sort of SPSS sorts of depths. We targeted off this algorithm, we found relative 5.5 quasars, and we went back and looked at the spectrum. So at Sloanish depth, I suspect at Des depth, that's good enough. But it has problems. And those problems are things, that suction is broken here, because I assume when I'm looking at this thing, that this and this object are equivalent, and I get something from each side. So I don't want to go into the details of this particular algorithm, but there are problems coming out of it which we're going to have to deal with. They get worse. Here's an example where you end up with things that look like this. I think I've zoomed in on that. Here's this object. You get stuff like this, but also things like this, which you can't see. But there's lots of length, no surface brightness fast. So, and things like that, where you rip the little flux out of the galaxy. That particular one I know how to fix. So, why am I showing you this algorithm isn't good enough? It's because though I have good ideas of how to make this better, they're going to make stronger model assumptions. And that means that the output catalogs that we're trying to do galactic science of are going to have deeper assumptions than you would have liked that go into the measurement. I don't see a way around it. When your eye looked at those very crowded cluster fields back here or there, about that one, you said, oh, I know what to do because that's an elliptical galaxy and that's an elliptical, that's a star and that's an asteroid. And I would take that apart based on that hypothesis. But the code has to agree with you in some sense. And the more strongly I agree with Bob, the more the output catalogs depend upon that being a good approximation. And the trade-off there is tricky, and it's a scientific trade-off. So the reason why this slow dynamical, this really weak hypothesis was that it was the weakest, it was the most agnostic way, it was the weakest prior essentially on the data. For lensing, you may or may not want to stick. I make these models and I use those to split the flux. There are people, and Jim is one of them, not here today, and certainly some of the best group doing lensing say, I don't want to know about what the objects look like, although Richard does. I just want to know what the model fit was. And I'll measure the moment from the model. I'll just fit elliptical things. And for some problems, I'm sure Jim is right. And for other problems, where you care about the morphology, you want to know about the spiral arms, you want to know about the Gini parameters, and you want to make things like petrosium fits, which are kind of useful, but they're kind of non-parametric, then you do need these pixel decomposed images. And the trade-off between how many measurements we make on the pixel decomposed images, which I agree we have to make available, and how many come from the simultaneous model fits to everything, is a scientific question. Which delivers better science? If you're interested in low surface brightness junk around things, then the takeaway story here is Jim's model fit approach isn't going to do it. Robert's give me the images is good, but he has to sort out this way of not ripping the outsides of my galaxy apart. And then, of course, you may be thinking, what about H2 regions? You're right. It's very easy to remove flux from H2 regions because they look like stars. And then you say, wait a moment, there's color information here. What happens if I make sure that things that have the same color are treated differently? Then I say, no. H2 regions don't have the right colors. So then I say, oh, no. In that case, I want to cluster things that have the same photometric redshift, perhaps. Or I want to discard things that have the colors of stars in the Milky Way. And maybe that's the best thing to do. So there are a lot more kind of trade-off-y things. And if we weren't dealing with objects that looked like this, then I wouldn't have to get into those when I'm building catalogs for the community. But in fact, there are trade-offs. And I don't know how to make them. I'd love to get input from my colleagues in Europe and also the States, because they're also painters, as to how we can maximize the scientific utility. And then I'll shut up and ready.
Thank you, Robert. Okay, so I think we have about 15 minutes left. Are there any more questions for Robert? We can always discuss them offline. Yes. So I think one comment we were discussing was the land lecture. So I think it worries me that given the fact that low surface science is going to be, almost a new type of science, which is going to be enabled by LSST, we actually don't have any machinery to
10-degree scales or 100-degree scales that have low surface brightness stuff and the cirrus. So that part I think I got right. I got a first argument from right here.
It's possible.
Yeah, that I can do. I know how to do that. How we maximize the usefulness of that, I don't quite know. And Mario didn't include any information about that in the DPDD. I think I must read back in a moment. But for example, there is going to be processing which is relevant to that. And this gets back into what the intermediate data products are saying. I think I mentioned this one the other day. So when I'm picking apart this group of 3 objects, I don't really care about the fact that we're labeling a small fuzzy thing over here. And if you just treat all objects equally, that burns infinite amounts of memory. So we're going to be doing a hierarchical decomposition of these objects anyway. Think wavelets. I'm not sure I'm going to use wavelets. I don't like them because of translational invariance problems. Maybe it's the right approach. If we're doing hierarchical decomposition problems of all the objects, we may be able to cheaply, and therefore I can afford to do it in Modulo database side, give you some summary of the overall gross properties of things. At the same time as saying, you know, this thing plus this thing plus this thing and this thing. So rather than, what I did in this firm we're doing at ScreenCam is to measure the properties of the parent, so probably this thing, the brightest object, plus each individual thing. But you can imagine more nuanced versions of that, where you get some more interesting properties of the overall object. You could include the low surface brightness wing, and will be useless for clusters of galaxies. I still measured them. So we can, I think, with input from the low surface brightness people, and they say, if the thing looks like this, what summary statistics for the parents do I want? Because you don't trust me to de-blend stuff with trails and tails and junk and garbage like that. So there are opportunities.
Maybe we can use these types of images which observe those subscribers and then just crowdsource quantification of those. I mean, with regards to we can literally get people to trace out the tails and then create new stuff.
Yeah.
That's not pretty.
No, I mean, just one thing we did once in Galaxy Zoo, which was fun, but we never actually used the data, so I'm a little hesitant about advertising. Well, not just that, but we also showed people images and asked them to identify errors in the parameterization of galaxies. So, for example, we would draw over the top the ellipse of the galaxy that the software that Robert's software had determined, and then said, is that a good representation of the galaxy we see? And we collected statistics on those sorts of how often did it get the right shape, the right size, the right. So you could do that. You could get that as an exercise.
I would remind you, low surface brightness, you can't really see it. Here's a spiral, and tracing that out automatically is getting difficult.
Yeah, it's very
It's getting really hard.
But you could do this with maybe
You get to do
where you can draw.
cluster zoo. There's another nice one in here somewhere. Cluster zoo, I can imagine, and if I can implement good ideas, it look really nice and bright in the galaxy.
That's going to be level 3.
Yeah, it's going to be level 3, but I may be able to give you a few numbers that say what's worth looking at.
Yeah.
There's an awful lot of data. This thing I'm scrolling around is 1.5 degrees, I think. And your eye looks at it and says, but all of it is interesting. I mean, I can zoom that far in and it's still interesting. So whether the Galaxy Zoo will scale without extra information coming from the pipelines, I don't know. We can now see those interactions.
So one point that a lot of people make is that Galaxy Zoo can't process this kind of this is what you predict. But is that strictly true? Because the classifiable subset of galaxies are still going to be things which are going to be low redshift and bright, right? So once you've done that, it's just it's 18,000 square degrees as opposed to maybe 10,000
trivial task to tell you what's interesting, unless you scan the whole sky. Maybe that's a thing to do. That's about 1.5 degrees.
Sorry, when you say interesting there, Robert, are you using sort of astronomically interesting or algorithmically
No,
interesting?
astronomically
Okay.
interesting to individual scientists, to particular sciences, to then go into galaxies.
My experience with Galaxy 2 is that we should not underestimate what people find interesting. So they will look at a lot of boring things and provide information on those boring things if they feel it is worthwhile.
No, that's a merge in consider my screen. No, I agree with that. The problem is that if I'm interesting to the scientists.
Okay.
If they have to go through 100 million objects to find those, that's probably beyond the scale of galaxies. If they have to go through half a million objects, we can make them do it.
Yeah. Especially if you explain why it's interesting to your science.
Yeah.
And it might be saying, I need to find the 1 in a million. And they're willing to help you find the 1 in a million if you've sold them that the 1 in a million is a Nobel Prize piece of research.
So I would like to come up with, I think the most we can do in level 2 is to try to find the right filters that make that a 1 in 100,000 task, not a 1 in 100 million task.
What exactly? When you talking about that, are you talking about just classification, or are you talking about very special objects?
I think we could have a whole day on crowdsourcing scientific information from LSST. And it could be checking imaging, it could be checking parameter estimations, it could be finding interesting sources, it could be measuring morphologies, it could be training samples for machine learning. We're not going to solve it in 15 minutes, but I think we could have a really interesting
Now,
day.
LSST is spending some money on this.
Yeah.
We have an EPO effort, Chris
Yeah.
Talks involved.
No, Chris?
Yeah, I will. So, they're a UK involved. So, if we can leverage some of that to science as well as to do K through 12, that would be good. In about 12th grade.
So maybe we should think about doing that at Oxford, maybe finding an hour, a couple of hours.
Yeah.
And you're also using
Yeah.
you're going to be there when you're spinning up.
I'll be there.
galaxy, it is disrupted by tidal forces, and the rings start to really oscillate the potential well of the host galaxy, and the shell edges are made of stars in the apocenters of their orbits. Shells are useful features because they allow us to constrain the gravitational potential of the host galaxy by the shell identification method, which is described in my poster. The poster also explains how to determine the time since the collision, which is important for investigation of how galaxies assemble. What is not covered by my poster is that different shell morphology is expected in Newtonian dynamics with dark matter and in modified gravity theories, which is what we currently work on. The biggest problem with shell galaxies is that their good images are missing. Good images in this case means that they need to be wide field, and the big source of images of shell galaxies are photographic plates, because shell galaxies were mostly popular in the 80s of the last century. But these images are shallow from today's point of view, and moreover, the galaxies are overexposed in the center, so that the shells in the centers are not recognizable. Other big source of images of shell galaxies is slow digital sky survey, but this is again shallow because the most images in this survey has an exposure time of around 2 minutes. Nice images come from the Hubble Space Telescope. They are sufficiently deep, but they capture only the centers of the galaxies. The current best source of images of shell galaxies is the Canada-France Hawaii Telescope. Here the problem is that only 2 little suitable shell galaxies are in the database, and moreover, the images suffer from optical artifacts which are bright halos around stars, which complicate the detection of shells and other tidal features. So when we have the images from LSST, we will have a great number of deep and wide field images, so that we will be able to determine whether the shell morphology corresponding to Newtonian gravity with dark matter is more frequent than the morphology corresponding to modified gravity, so that we could compare between one of those scenarios. We will be able to investigate the gravitational potential of a large number of Earth-like galaxies. It is quite difficult to investigate the potential of Earth-like galaxies up to large radii especially, and then we can use the LSST images for investigating the frequency of the mergers producing the shells, which provides a test of cosmological models. And that's all.
Questions? I have questions. So, up to what redshift do you be able to use LSST to do the shell size?
This is what I haven't estimated yet, but it will be even useful to have the images of nearby galaxies, because, as I say, there is a low number of good images of shell galaxies. So.
Does it mean the depths or low redshift galaxies? That's a big thing.
Apologies, I might have been reading my email when you said this. So if you've said it already, sorry. I'm intrigued by, when you say modified gravity there, are you specifically talking about things like MOND, or are you talking about fifth forces to understand
Yes,
the
what I
acceleration?
speak. Good question. I spoke here about MON.
About MOND,
Because
okay.
I have worked on MON for several years, and I'm even not sure if there are any simulations of galaxy interactions in other modified gravity theories. I cannot recall any, but there are differences in the simulations of galaxy interactions in MON and in Newtonian dynamics, and the difference, one of the most important differences is that the dynamic of friction during the galaxy interactions is lower in MON. And
Are those hydrodynamical simulations you're talking about?
yes, some of them were hydrodynamical, some of them contain common stars.